You know, the universe, it runs on rules, a set of fundamental, absolutely unbreakable rules. And in the world of chemistry, there is one law that governs everything. I mean, every single chemical reaction, from a star-going supernova to a simple antacid tablet fizzing in a glass of water, has to obey it.
And here it is, spelled out for us by the father of modern chemistry himself, Antoine Lavoisier. Now, this isn't just a friendly suggestion. It is the law. You can't just magic matter into existence, and you can't make it vanish into thin air. It just changes form. This idea is the bedrock for everything we're about to get into.
So the official name for this is the law of conservation of mass. The easiest way to think about it is with Lego bricks. In a chemical reaction, you don't lose any bricks, and you don't find new ones out of nowhere. All you're doing is taking your structures apart and rearranging those same bricks into something new. The number and type of bricks you start with has to be the same as what you end up with.
So if these reactions are just rearranging atoms, then chemical equations are like the official receipts. They're the bookkeeping that tracks every single atom, proving that the law was followed. But what happens when you look at the receipt and the numbers just don't add up? Let's take a look at maybe the most famous reaction on the planet: hydrogen and oxygen getting together to make water. Seems simple enough, right? H2 plus O2 gives you H2O. But wait a second. If you look really close, there's a problem hiding in plain sight. Let's do a quick atom inventory. On the left side, the reactants, we start with 2 hydrogen atoms and 2 oxygen atoms. Simple. But then you look at the right side, the product, and we have 2 hydrogens and, wait, only 1 oxygen? Uh-oh, our receipt is totally wrong. The books don't balance. Which leads us to the big, obvious question: where did that other oxygen atom go? It can't just disappear, right? The law of conservation of mass says so. This is exactly why we need to balance chemical equations, to solve this little mystery and make sure our chemical receipt is telling the truth.
All right, so it's time for us to become cosmic accountants. In this section, we're going to fix our broken receipt. We're going to learn the simple, systematic way to make sure that universal law is always satisfied. First things first, we need to know the tools of the trade. We've got coefficients. Those are the big numbers we can write in front of a molecule. Think of them as multipliers. They tell us how many of that molecule we're working with. Then you have subscripts, the little numbers inside a formula. And this is the #1 rule. You can change the coefficients all day long, but you can never, ever touch the subscripts.
And here's our roadmap. It's a super simple 4-step process. First, write down the equation. Second, tally up the atoms. Third, you start adjusting those big numbers, the coefficients, to get things even. And finally, you do one last check to make sure everything's perfect. That's it. Let's try it on our water problem.
Okay, so steps 1 and 2 are done. We know our oxygen is the problem. 2 on the left, only 1 on the right. To fix this, we need to get 2 oxygens over on the product side. Now remember, we can't touch that subscript in H2O. So our only legal move is to put a big coefficient, A2, in front of the entire H2O molecule.
So let's update our inventory. And hey, great news, our oxygen is balanced. We've got 2 on the left, and that coefficient gives us 2 on the right. But look what happened. In fixing the oxygen, we now have 4 hydrogens on the product side, but still only 2 on the reactant side. See? It's like a puzzle. Sometimes fixing one thing messes up something else.
But that's no problem at all. We just repeat the process. To fix the hydrogen, we need 4 of them on the left side to match the right. So what's our move? We just go over to the H2 molecule and place a coefficient of 2 right in front of it. And now it's time for the final check. Let's do the math. On the left, 2 times 2 gives us 4 hydrogens, and we've got 2 oxygens. On the right, 2 times 2 is 4 hydrogens, and 2 times 1 is 2 oxygens. And there it is. 4 hydrogens on both sides, 2 oxygens on both sides. It's perfectly balanced. Yes, success! The receipt is correct, the books are balanced, and most importantly, the law of conservation of mass is satisfied. This equation now tells the true story of what's happening. 2 molecules of hydrogen react with 1 molecule of oxygen to create 2 molecules of water. Every single atom is accounted for. Okay, now that you've got the basics down, let's level up a bit. We're going to talk about the single biggest mistake people make, and then I'll share a few pro tips that will help you tackle even the most complicated equations like a total pro. Rule number 1, and I cannot say this enough, never, ever change the subscripts. Why? Because if you change H2O to H2O2, you haven't balanced anything. You've changed the identity of the molecule itself. You've turned water into hydrogen peroxide. That's not bookkeeping. That's rewriting what the reaction is even about.
All right, here are a few tips to make your life way easier. When you see a really complex equation, start with the metals first, then the other nonmetals, and always save hydrogen and oxygen for the very end. They tend to pop up all over the place. And here's a huge time saver. If you see a group of atoms like sulfate, SO4, and it's on both sides of the equation, don't break it apart. Just treat that whole group as one single thing you need to balance.
So you might be wondering, why have we spent all this time learning how to be atomic accountants? Is this just some random exercise for a chemistry class? The answer is absolutely not. Let's take a look at how this skill connects directly to the real world in some really surprising ways.
See, knowing the correct ratio of reactants to products, this field is called stoichiometry, is absolutely essential for pretty much every chemical process you can imagine. If you want to manufacture a medicine, produce fertilizer, or even process food, scientists need to use balanced equations to figure out the exact amounts of ingredients to use. It's literally the recipe for reality.
In fact, your life depends on a balanced equation right this very second. This is cellular respiration. It's the precise, perfectly balanced reaction that your body is running over and over again to turn the food you eat and the air you breathe into the energy that's keeping you alive right now.
Or take a look at this massive industrial reaction. When you mix quicklime with water, it creates something called slaked lime, and it releases an incredible amount of heat. To do this safely and to create a stable product for things like cement and mortar, engineers have to rely on the balanced equation to get those ratios exactly right.
And honestly, the examples are just everywhere you look. The slow, patient rusting of an iron gate, the absolute miracle of photosynthesis that creates the food we eat and the oxygen in our atmosphere. All of these processes are governed by the strict mathematical rules of balanced chemical equations.
Which brings us right back to where we started. This isn't just some rule for a chemistry lab. The conservation of mass, which we represent with our balanced equations, is a fundamental operating principle of the entire cosmos. From the biggest, hottest star to the tiniest cell in your body, matter is never created or destroyed, just rearranged.
So, you see, you haven't just learned a skill for chemistry class, you've actually learned to read one of the fundamental rules of the universe. You now know how to do the bookkeeping for the cosmos to make sure every atom is always accounted for. So the only question left is, what will you understand next?